Okay, in this video we're going to explore the idea of conservation of charge. It's an extremely important idea. It's one of the most fundamental conservation laws that we understand in physics. Maybe the most important one that we've learned is conservation of energy. And if you look at how conservation of charge is expressed, you'll see a lot of similarities. We say that energy cannot be created or destroyed. We say the same thing about charge. Charge cannot be created and cannot be destroyed. There is no factory in which we are creating charge, and there is no place where we are destroying charges so that they no longer exist. One difference, though, between conservation of charge and conservation of energy is that charge can only be transferred, whereas with energy, energy was able to be transformed into many, many different forms that we talked about. But with charges, there is only the one form, the positive or negatives. Remember, positive and negatives are kind of like the right and left hand version of charge. There's sort of a in-between which has no orientation, and then the positive and negative charges are essentially like this property that has a kind of handedness. The positive and the negative are similar. They're almost the same, except they're exact opposites of each other. So this idea that charge can be transferred is really important in terms of understanding how do things get charged in the first place. And so let me show you several examples that will hopefully help it make it clear about how this idea of conservation of charge can be applied both numerically but also just from a conceptual standpoint. So just like we've done with a lot of the conceptual things that we've looked at so far, let's start by using a pith ball. I'm going to use in this case a pith ball which has actually already been charged. So maybe a plastic rod came in and charged this guy so that he had a +4 charge. So there are +4 charges on this pith ball. Now I'm going to combine that pith ball with an identical sized pith ball that is neutral. Okay, and between the two of them, they have 4 total charges. Okay, now all I'm going to do with this thing is I'm going to bring these two together so they are going to make contact, and by making contact, that is going to allow some of the charges to be transferred from one of the pith balls over to the other pith ball. Okay, now again, did not create anything. These were not made. They were just simply transferred from the pith ball on the left to the one on the right because the positive charges don't like each other. They want to separate. Now, at the microscopic level, is it really that 2 positive charges moved over to this pith ball? No. This is like a level 2 explanation. You say 2 of the positives went over here because they want to repel each other. They want to spread out as much as they possibly can because they don't like each other. But in terms of explaining it, is that really what happened? It's really not the positives that do the moving. Because remember, the positives are in the protons that are tucked deep in the nucleus of the atom, and those don't move anywhere. The atoms don't leave their location. So what really happened was that some of the electrons from this pith ball, because they were attracted to the positives on this side, some of them left. Now eventually, so many of them would leave that eventually you would have the same amount of charge on both, and then there's no reason for electrons from here to go to this pith ball. There's no reason for electrons from here to go over to this pith ball. Now things are kind of balanced out. This is the best that they can do. But what you will notice is that there are still 4 charges, right? I did not add any new charges. I didn't take away any old charges. So in this case, it's 2 plus 2 is 4 charges total. And even once we separate these two things, once the 2 pith balls are separated, they still are going to retain that charge. So unless something comes along and takes away that charge, they are going to have 4 charges because that is what was in the original situation. No matter how many times I touch another pith ball to these things, the 4 charges are still going to be present. It's just that they may spread out because they don't like each other. Like charges want to repel. Let's look at a little more challenging example. Let's say that we had 3 pith balls this time. They're not touching each other yet. Okay, and in this case, I'm going to draw a certain number of charges on these guys. So let's say that this guy on the left has a +6 charge, +6. The guy in the middle, he's got 2 negative charges, so that's -2. And then the guy on the right-hand side, we'll say that he has 5 charges. Right, remember, they're all nice and evenly spread out, +5. Okay, well, what's going to happen when we make these things all touch? Well, if you just look at what is the total amount of charge that we have, right? Just like I would do with energy, I would say, well, what's the total amount of energy that I have? And then we think about how that energy has been transferred or transformed into other forms of energy. Now, same thing. Once these 3 all come in contact with each other, charges are going to start to move around. The negatives like the positives like the negatives. People are going to start to move around. But the total amount of charge in this system of 3 pith balls should not change. So let's just take a look at what was the total. We had +6, -2, that's so that's +4. and 4 plus 5 is plus 9. So right now we have a total charge of plus 9. So what will happen when the 3 pith balls are forced to come in contact with each other? Then what you're going to see is that the charges are going to they're going to distribute themselves. These negatives will be neutralized by one of the charges from the other 2 pith balls. And so that's going to leave us with this. There will be 3 positive charges which cannot be counteracted. They cannot be canceled out because there's not enough negative charges. So if you look, I have a total of 11 positives. Right, but then there's the 2 negatives. So those 2 negatives are going to neutralize 2 of the positives, leaving only a total of plus 9. So when the pith balls come together, it's going to be 3 plus 3 plus 3 to still give me the plus 9 charge. So charge has been conserved. Yeah, I don't see the negatives anymore, but the total charge in the system is still conserved and is still exactly the same as it always was. Let's look at one last example where we actually start with a neutral object, and this has something to do a little bit with the idea of charging, which we've already talked about, the different methods of charging. But let's say that, for example, we're going to use in our lab, we're going to use 2 pieces of tape. They're going to face the same way, so you're going to have one piece of tape that's going to be stuck down on the table or on a book or something like that. You'll take a second piece and put it directly on it, facing the same way. Don't put the sticky sides together. That's not going to come apart very easily, and it's not going to pick up a good charge. What we need is the sticky side of the tape to be touching against the back side of the other tape, and then when we pull these 2 things up, we can rip them apart very quickly, and what will end up happening is the 2 pieces of tape will exchange some charges, and we will end up with 2 charged objects. So as it is right now, there is 0 charge on this piece of tape. We have 2 pieces of tape. They're facing in the same direction. They've been stuck together. And now we're going to take the 2, we're going to grab them by their little tabs, and we're going to pull them quickly apart. And when they do, one of them will take charges from the other guy. And what we will end up with is something that looks like this. So we'll have the 2 pieces of tape. And let's say, for example, that this guy takes on a positive 5 charge. Okay, well, what's going to happen on this guy? Well, where did this guy get his positive? He got him from this guy, right? So the 2 things, we're going to have identical charges, but one of them is going to have a plus 5, one of them is going to have a negative 5, and when I look at what's the total charge, what's the total charge on the, it's still 0, right? I did not create any charge. I didn't destroy any charges. All I did was transferred 5 electrons from this piece of tape over to this one to give this guy a minus 5 total charge and this guy a positive 5 total charge because of the individual charges. It would never be something where this was 0 and this was 5 and this was 3, or this was 6 and this was 9. That would violate one of the most basic principles in our universe, and that is the idea of conservation of charge. The only thing we can do with charge is we can't create it, we can't destroy it, but we can move it around, and that's basically what we do. Under different circumstances, when you, let's say, for example, rub your feet against the carpet as you walk across it, you are just transferring charge, not creating anything. You're just pulling some charge off of the rug, and as a result, that rug is taking on a charge, but so is your foot. And the 2 of those things would be still overall neutral. Your foot and the carpet would have the same number of charges. That's a great example of the idea of conservation of charge. Charge is transferred, but we don't destroy it or create it.